All right, this video is going to be talking about tangents, going more into detail with what happens with tangents on circles. We've talked about several different things about what happens with chords. Now we'll focus on this. In a plane, a line is tangent to a circle. So we've got a tangent just touches, okay, just brushes by and just barely touches that circle at one point. If and only if it is perpendicular to a radius drawn at the point of tangency. We need to remember that perpendicular is going to mean our 90 degrees. Very important so that we see we have a right angle. The point of tangency is where the tangent touches the circle. Okay, so point A would be your point of tangency. So let's go ahead and start off with number 1 using this information. So again, this is a biconditional, meaning that a line is going to be tangent to a circle if we notice that we've got this 90-degree angle here with the radius, as well as if we see that we've got this 90-degree angle with the radius, we automatically know the line is tangent. So on number 1, we're going to see that OT is 5, so we need to draw in that segment here. This is going to be 5. And we're going to have XT right here, this segment is going to be 12. And OX, which we'll draw in, is going to be 13. What we're going to do is try to figure out if line YX, or XY it says here, is tangent. Is it perpendicular to our radius segment OT? How we're going to do this is we are going to test to see if triangle OTX is a right triangle. If it is a right triangle, then it is going to be tangent. If it's not a right triangle, it's not tangent. So basically what we're asking is, does 5 squared plus 12 squared equal 13 squared? And we did this in our previous chapter, testing to see if we have a right triangle. We're looking at, do the 2 legs squared and added, do they equal the hypotenuse squared? So we'll go here and say, okay, we got 25 plus 144, and if this is a tangent line, then this should equal 169. When we add these, we find out we do have a right triangle. So the answer to the question is yes, but we want to make sure that we're putting in our notes the explanation right here, explain your reasoning. And this is our explanation. We have that triangle OTX is a right triangle. So we have this right triangle here, making OT our radius. Sorry, I forgot the segment bar. Segment OT, the radius, perpendicular to segment, or we can even say line YX. So YX is going to be a tangent because we have this right triangle. Go ahead and pause and have that written down. Number 2, we're going to do the exact same thing we just did. We're going to see here that OT, we'll draw it in, is going to be 4. YT, right here, is 8. And OY, draw that in, is 10. We'll go ahead and complete the same exact thing, asking ourselves, does 4 squared plus 8 squared equal the longest side squared, 10? When we go through, 4 squared is going to be 16, 8 squared is 64, 10 squared is 100. When we add the 16 plus the 64, we're going to end up with 80. So these are not going to be equal, therefore we do not have a right triangle. And we'll go ahead and write in our explanation for that now. So our explanation, that segment YX, right here, or line YX we should say, since it is a tangent, is not tangent, okay? Because segment OT, our radius, is not perpendicular to line YX. Because we proved over here we do not have a right triangle, therefore we cannot say that line YX is tangent. Number 3, we'll go ahead and solve some things here. We are seeing that given line xy is tangent, so they are telling us now it is tangent, we're not proving it, to circle O at point T. There's your point of tangency. If the length of OT, draw in that radius, is 18, and OY, draw in what's going to become our hypotenuse, is 24. So we have our 90 degree because now we know it's tangent, so it is going to be perpendicular to the radius. We're going to figure out what YT is. So right here, the other leg, the missing leg of this right triangle. Please note we do want this in simplest radical form, so we will not be plugging the square root into our calculator, okay? So if we label this as our missing, well, I'm not going to put an x there because there's already an x there, but we're going to be finding YT. So we'll go ahead and say that's our missing leg, x squared, plus the other leg of 18 squared, all equal to 24 squared. Missing a leg, we square the numbers, subtract, and then we're going to simplify the radical when we take the square root. So we have x squared plus 324 will be equal to 576. We subtract that 324. X squared is going to equal 252, okay? And I still have students who are telling me the answer is 252. It is not. That is x squared. We need to take the square root. So we're going to go ahead and simplify our radical. I do the division tower, dividing by prime numbers until I have a prime number at the top. So I'm going to go ahead and start with that. I'm going to divide by 2 to get 126. I'm going to go ahead and divide by 2 again to get 63. 63 will not be prime, but I can't divide it by 2 anymore, so I'm going to move up to 3. And I could divide it by 3 to get 21. 21 is still not prime. I could divide this by 3, and I'm going to get 7. 7 is a prime number. I'm done building the tower. And I've seen students kind of start drawing this next division. Don't, because then you may not see that 7. We want to stop the division tower once we have that prime number up top. So with our radical house, here's a partnership of 2. 2 goes outside. Here's a partnership of 3. So a 3 is going to go outside. And then 7 is going to be all by itself inside since it has no partner. So 2 times 3, our missing side is going to end up being 6 square root of 7. Final answer. All right, let's go ahead and take a look at number 4 here. Number 4, we are going to solve for x if QS, right here, is tangent to circle R. We're being told it's tangent. We conclude we have a right angle. So solving for x is going to be right here. So what we need to do is we need to go ahead and look at our Pythagorean theorem, remembering that here, this is going to end up being our hypotenuse. We need to add these two parts together to get x plus 2. So we'll go ahead and what else we want to notice here, guys, is if you cut off this part right here, we're going to see that RQ is the radius. Well, from R down to here, this part of the hypotenuse is also the radius. So that means if this part is x, our radius is also going to be x. So we can go ahead and set up with our legs here, x squared plus 4 squared equals the hypotenuse squared. Now, watch what we have here. We have an x plus 2, so we have to do x plus 2 in parentheses with the squared outside. We're going to wind up having to distribute that exponent, and we'll do that here in a minute. Let's go ahead and bring down x squared plus 16 equals, now when we distribute, the x is going to be squared, so we bring down x squared. When we distribute the exponent to the 2, 2 squared is going to end up 4. Let me rewind real quick. I'm actually going to show you the Punnett squares, what they do in biology, and they also do this in algebra. Let me go ahead and draw that out. Change my mind halfway through that. When we have to square the the x plus 2. This is where we go here with this, which you learned in algebra. And we need to fill in all 4 boxes so we can figure everything out over here. We've got an x times x, which will give us that x squared. We have that x times 2, giving us 2x. Over here we have another x times 2, giving us another 2x. Look right here, we have a total of 4 x's. And then we have our 2 times 2, giving us 4. So I want you to see everything that's going on over here, all right? Now, we have not done anything like this in geometry. We've got this x squared plus 4x. What are we supposed to do? Oh my goodness. Well, watch what ends up happening on this problem. We have an x squared on both sides. So if we move one, let's say we move this x squared, we're going to subtract it, right? Well, guys, they end up canceling out anyway. You don't have to deal with that anymore. We actually don't even have to do any sort of square root on this problem because these will cancel. We'll bring down our 16 equals. Now we're left with 4x plus 4, okay? And now we just have our 2 steps. Subtract the 4 from both sides. We're going to end up with 12 equals 4x. And then divide by 4. We're going to find that x is going to be equal to 3. So we didn't have to get too algebra-like in there. So here on the next page, just go ahead and write out that definition. Probably should have it at the beginning, but oh well. That our tangent lines define that it's going to be a line that touches a circle at exactly 1 point, as we discussed on the previous page. And so now we're going to talk about one more thing with tangents, and this one's pretty cool because there's not a whole lot of difficulty going on with this exact theorem here. We have 2 tangent lines that are going to intersect, and they may look like either one of these, but I want you guys to see we've got these 2 lines that are going to come through that are going to barely touch the circle, and they're going to intersect here at point B. Sometimes these examples, a lot of times, I'm going to say most of the times, it's not going to show the entire tangent line. It's going to cut it off right here and just have it as 2 segments. And what ends up happening is these 2 tangents are going to be congruent. So these 2 tangent sections out here between where it touches the circle and the intersection will be congruent. So we're going to go ahead and name these 2 tangents. We've got here line AB and line CB. So as I just said, your tangent intersection formula, when 2 tangent lines intersect, their lengths are going to be equal. All we say for this is tangent equals tangent. Set them equal to each other. That is it. So when we go through with number 5, we're going to see here we have 2 tangents. They do not go inside the circle. They just stop right there. As we discussed, that's how we'll be seeing it. So that means they are going to be congruent. So we're going to set them equal to each other. So we have this 2 parentheses 2x plus 1 is equal to 14. So let's go ahead and do our distribution with the 2. 2 times 2x giving us 4x. And then 2 times 1, a positive 1, we're going to get 2. And now all we need to do is subtract the 2 and then divide by the 4. And we're just going to solve for x on these 2 right here. Okay. All right, number 6, I encourage you to stop the video, I'll pause it, and do this on your own. We're doing the exact same thing, we just don't have the distribution, okay? We've got 2 tangents that are going to intersect at point B, telling us these are congruent, so set them equal to each other. 3x minus 2 equals 2x plus 5. And if you didn't already pause it and do it on your own, please pause it now, solve for x on your own. And we should have ended up with 7. Okay, so let's talk about some other things. We're going to end up, this diagram on number 7 is a circle inscribed inside of a triangle, or we could say the triangle is circumscribed about the circle. What ends up happening is we end up with all these tangents, okay? Let's go ahead and first label what information they gave us. In the diagram, RT, this entire section right here, is going to be 12. RH is 5, so we find right here, RH is going to be 5. And MT is 21. So we look over here at MT, this entire length is going to be 21. We want to find the perimeter of the circumscribed triangle. Now to do that, we have two of the three sides. Ladies and gentlemen, this is not a right triangle. Do not attempt Pythagorean theorem. Do not attempt special right triangles. Do not attempt any sort of trigonometry. We're going to use what we know about our tangents being congruent, and also do some adding and subtracting, some segment addition postulate. What I want to do first is I want to focus on these two tangents. Okay, we have segment RH and segment RD. They are going to be congruent, so that means RD is going to be 5. This is leading us to figure out what segment DM is, so we can figure out what the entire side is. Now, we need to start moving around. If we focus on segment RT right here, the entire thing is 12. We'll define HT, we're working backwards with segment addition postulate. We're going to take the whole thing of 12, subtract that 5, and we're going to find out that HT is 7. Now moving even further, we've got another pair of tangents right here. HT and TA are going to be congruent also, telling us that TA is 7. Okay, now looking at this side length right here, we're going to do the exact same thing we just did for RT. We're going to work backwards from segment addition postulate, and we're going to take that entire thing of 21, get rid of the TA 7, so that we can find out AM is 14. Okay, slowly moving around. Now we focus on our last pair of tangents. We have AM will be congruent to DM, telling us that DM is 14. Now that we have all the little tangent pieces, we can now conclude the third side that we were missing is going to be 19. So finding our perimeter, all we need to do is add up those three sides, 12 plus 21 plus the 19. We're going to find out that the perimeter will be 52 centimeters. Go back and watch that again. That's why I use my Post-its. That's why I like the document camera, so I can cover things up. Hopefully that clarified and made sense to you guys. All right, number 8. Another thing we're going to be working with these tangents. In the diagram, segment NM and segment QN are tangents, okay? And they're tangent to the circle. The radius of circle P is 5 centimeters. So right here, segment PM, the length is 5. As we learned, the line is tangent if it is perpendicular. Well, we just were told that MN is tangent, and so its connection to the radius will be a 90-degree angle. We're going to need this, okay? And then the last bit of information they give us is the length of MN is going to be 12. We want to find PN. PN is not in this diagram, so we're going to draw it in right here. So what we are doing is we are going back to our right triangles that we did on the previous page. So this is going to be our missing side. I'll put it as X. This is going to be the hypotenuse. So when we use our a squared plus b squared equals c squared, we plug in 5 and 12 for our legs. And we'll go ahead and take our steps. 25 plus 144. Keep bringing that squared down. We end up with 169 equals c squared. And when we take the square root, it doesn't tell us to round or anything. Again, this is going to end up being a perfect, square root of 169 is a perfect square. This ends up being our missing side. I know I put a X up here, but our answer is 13. Okay, so we're just kicking back, making sure we didn't forget we have these right triangles when your line is tangent, it will automatically be perpendicular to that radius.